Hello everyone, my name is Hari Om. In this talk, I am going to talk about our ongoing work on multi-level regularization strategy for image registration. This is a joint work with Professor Jan Morszewski from University of Lübeck. I will start with a very brief introduction to image registration where mainly the focus will be on registration of a dynamic image sequence. Then I will point out the state-of-the-art spatio-temporal regularization strategies. Then I will explain our proposed multi-level regularization strategy. This strategy has mainly three ingredients: the discretization of spatio-temporal space, interpolation method for deformation fields, and a stopping criteria. After that, I will show the effectiveness of our scheme on a four-dimensional optical coherence tomography dataset. And at the end, I will conclude our talk. So in this slide, you see two videos. On the left-hand side, you see an unregistered image sequence, and on the right-hand side, you see a registered image sequence. This is the scan of a human eye. And because during the scanning, the human eye is not stable, it moves. And that is why we see the fluctuations in these scans. The goal here is to correct these fluctuations and obtain a stabilized scan such that we can do some further analysis. And one of the analysis is the blood flow along these RP layers. So in order to stabilize the motion, we do the image registration where we want to find out the transformation field such that if we apply the transformation field on the images in the given image sequence, after the transformed images we obtain a stabilized image set. To achieve our goal, we construct a registration model based on a variational setting. It has mainly two components, the distance measure and a regularizer. So d of y represent the similarity measure and s of y represent the regularizer where we enforce the desired characteristics of the deformation field. So for an example, in our experiment, we use the Pearson correlation coefficient to measure the similarity between the transformed images in the given image sequence. Because these image sequences have some dynamic property, because the same object which is moving over the time, so the neighboring frames are somehow correlated to each other. So in this setting, it is meaningful to incorporate some kind of spatio-temporal regularizer. So one of the state-of-the-art way is to include two terms. The first term here enforces the spatial smoothness, and the right-hand side term includes the temporal smoothness. In our work, we are proposing to use the multi-level regularization to incorporate the temporal smoothness. That means we do not consider the right-hand side term, and that means so we have the beta equal to 0 equivalently. So before I describe the multi-level regularization strategy, I want to comment on what do we mean by temporal smoothness. At the top, you see the 8 consecutive slices of the 4-dimensional dataset. So these are the 2D slices of a 3D object. Visually, we cannot differentiate the differences between these slices. So this red curve shows the translation along the vertical axis. So as you saw earlier in the video, there was mostly the fluctuation along the vertical axis. As we see this red curve, which is the translation along the vertical axis, this seems to be quite a smooth curve. And if we see the translation between time instant 24 to 31, there are very small displacement here. And that is why we also do not observe very big differences in these 2D slices. So based on this graph, one can think about that if I know the deformation field at time instant 24 and the deformation field at time instant 31, then I can probably guess the deformation field in between the time instant. And that is the main idea which we are exploring here and building a multi-level strategy here. So what do we uh, do here is, so suppose we in this example we have 57 images. So instead of doing the registration of all the images at once, we start with the registration of 8 images. So we register 8 images and estimate the deformation field for these 8 images, and from that we get the deformation field that is represented by the blue circles here. The next step is to interpolate these deformation fields and guess the deformation field for all the other images in the given set, and that we use as a initial guess for registration where we take all the images in this example. So here I'm explaining only the 2-level temporal discretization, but it can be extended for more than 2 levels. So how we obtain the temporal smoothness here? So because of the interpolation, we are somehow incorporating the smoothness over the time, and that's the way we can understand that we are incorporating the temporal smoothness in this setting. So mainly in our strategy we have 3 ingredients. So the discretization of spatio-temporal space. So far we have discussed the utility of the temporal discretization, but in the next slide I will focus on the spatial discretization, which is very important component for image registration. The next ingredient is the interpolation method for deformation field. I will point out that we need a special care there, and then we will talk about the stopping criteria. So why we need the spatial discretization for image registration? So image registration is a highly non-convex problem. That means we have numerous undesirable local minima. So to illustrate this point, I take 2 images R and T. The T image is slightly shifted towards the right hand side. So we want to estimate this translation parameter. T of y represents the transformed image, and the D of y is calculating the similarity measure. So we will plot the similarity measure here corresponding to different y's. So even in this simple setting, we see that D of y has a lot of local minimas. So if my optimization algorithm starts very close to this local optimal point, then maybe my optimization algorithm stuck at this local minima, and it may not be able to reach to the global optimal point. So that is happening in the very simple example, and that's what we observe in the more complex examples as well. So in order to reduce these local minima, a very well-known strategy is based on image smoothing and the spatial discretization. In the next slide, I will illustrate this point more. So now what I'm doing here is that I take these 2 images, R and T. I construct a hierarchy of images. So as I'm going from left to right, I increase the smoothing of the image and represent the smooth image at the coarse resolution. So in order to register these images, we start from the right hand side. So first we take the over smooth images that is corresponding to the green curve in this plot. So we start the registration of these 2 images, and we get an estimate of the deformation field. If you can see it from here that it's already very close to the global optimal point. Now we use it as an initial guess and then register the images which are in the 3rd column of this sequence, and then we are getting more close to the desired global optimal points. So that's how we construct our registration scheme. So as you observed here that because of the image smoothing, our objective function also gets smooth, and that reduces the undesirable local minima. And as you also have seen here is that we obtain a quite outstanding initial guess for the final resolution, and because of that we need very less number of iteration, and that's the reason that we have the acceleration in our registration scheme. And because of the smoothing of the image, we can represent our image at the coarse resolution, and we also define our deformation field at the coarser resolution, and that also decreases the number of unknowns that we want to estimate. So now we know why we need the spatial discretization and the temporal discretization. Now we construct a discretization in this spatio-temporal space. So from top to bottom, we construct the spatial levels. So where we have the 2 by 2 image, then the next final level have the 4 by 4 image, and the next finest level has the 8 by 8 image. So this is just for an example to illustrate the concept. From left to right, we increase the temporal level. That means we start with the registration of 3 images. We include one more image, we register 4 images, and consequently we increase the number of images. And at the very end, we register all the images given in the image sequence. The arrow indicates the registration sequence. So first, we start from the top left. We register 3 images at the coarsest resolution. We get an estimate for these 3 images. We do the interpolation and register the 4 images. So in these 4 images, the first 3 images are included. And likewise, we go further. We obtain the deformation field at the coarsest spatial level, and we know the deformation field for all the images in the given sequence. And then we go to the next spatial level. So in this image registration sequence, the interpolation is one of the main important point. So at the coarsest spatial level, we perform the linear interpolation, but one can go for the spline interpolation and any other interpolation scheme. But at the finer spatial level, we need some spatial care, and we will illustrate this point later. Just to highlight that, we do the interpolation component wise. So for example, for the 3D data set, and if you assume that the transformation field is constrained to the affine deformation, then affine deformation will be represented by 12 components. So we are right now doing the interpolation of each component individually, but there could be a better strategy, and that is our ongoing work. So now start with the interpolation scheme at the coarsest spatial level. So here we are registering the 3 images. So the first registration will be performed for the 3 images, where the initial guess for the registration model would be identity map. So that means we assume that there is no deformation at the very start. Now we register 3 images, we get an estimate of that we represented by the eta. And in this plot, this is shown by the black circles here. To get an estimate for zeta, which will act as an initial guess to register the 4 images, we interpolate the deformation field, which we have calculated at the lowest temporal level. So that is represented by the blue dotted line here, that we use as an initial guess, register the 4 images, and then again we get an estimate, then we again do the interpolation, and likewise we go until the last temporal level where we register all the image sequence and obtain this red curve. Now we go to the final spatial level where, so for example, now in the previous slide, the image size was 2 by 2, now the image size is 4 by 4. So one of the important thing to notice that we already know the deformation field for all the images in the given image sequence at the coarse resolution, and that we want to use it now. So first we register 3 images. For that we use the deformation field which we have calculated at the coarse resolution. So that is represented by omega here, and that is the red line in this plot. Now we register these 3 images, we get an estimate which is an improved estimate, and that is represented by the black circles here, these black circles. Now as we did earlier, that one can probably interpolate again to get an estimate of zeta. But if I do the simple interpolation, then I'm not using the deformation field for the fourth image, which we have calculated at the coarse resolution. So in order to use that information, we solve a linear least square problem. So the first part of that, simply saying that the estimate zeta which you want to calculate is close to the black dots here. So the KQ is the image set which we use. So these are in our case we have 3 images which we used for the last temporal level. The second part of this least square problem is simply is trying to incorporate that the first order derivative of the red curve is close to the first order derivative of the zeta. And that's how we solve this least square problem to estimate the zeta. And then we register the 4 images and get a new estimate. And again, we solve the linear least square problem. And that's how we improve our deformation field estimate. As you might have noticed that we are calculating the deformation field for all the images. At least we have some estimate of the deformation field for at each temporal level for all the images. So that allows us to calculate the distance measure for the whole image sequence. So if we observe that our distance measure is not changing too much from one temporal level to the another temporal level, then we stop our registration process. And because of that, it might be possible that we may not need to register all the images given in the image sequence, and that reduce our computation time. So illustrate the effectiveness of our strategy, here we are taking the 4-dimensional optical coherence tomography dataset. This is a scan of the posterior of our eye. For these dataset, affine deformation is good enough to correct the motion. We use the image intensity as a feature to measure the similarity between the transformed images. Here we are taking the 129 images. We construct the 4 temporal levels. That means we start the registration of first the 17 images, then we register 33 images, then we go for 65, and then at the end we register 129 images. We define 3 spatial levels here. We compare 2 multi-level strategies. So the SPML is the spatial multi-level strategy where we do not perform any temporal discretization. And the STML is the spatio-temporal strategy which we proposed in our work. So these are the 2D plots. So the first figure is the unregistered image, and the middle one and the right hand side one is the registered images. So the horizontal axis represents the temporal dimension, and the vertical axis represent a line in the 3D space. So because the images are not registered, so along that line there is fluctuation, and that is why we observed a curved motion here, a curved structure here. And after registration, all the images are nicely aligned, and that is why we see the straight line for both of the registration schemes. So as we observe from these plots that both of the registration schemes are almost giving the same results. But there is a significant difference in the runtime. So here D1, D2 are the 2 dataset. SL represent the spatial levels. So we have 3 spatial levels for these 2 datasets. So the SPML scheme, which is based on only spatial discretization, takes 540 seconds, but the proposed scheme only taking 193 seconds. So that means we are getting a speed of around 2.8. And the similar behavior we obtain for the another data set where we get a speed of around 2.5. Now I want to show you the temporal smoothness part. So the blue line here is the results from the SPML scheme where we just simply doing the spatial discretization, and the red curve is coming from our proposed scheme. So as you observe visually that there are slight smoothness in the estimated field. So I'm just showing here the translation parameter from the affine deformation. To measure the smoothness, I'm taking the L2 norm of the first derivative of our deformation field. So from the spatial discretization scheme, this estimate is higher than the proposed one, and that also indicates that we obtain a smoothness in our deformation field. So in this talk, we are proposing a spatio-temporal strategy that exploits the temporal smoothness intrinsic to the given image sequence. We are suggesting the interpolation method, which is suitable to obtain the temporally smooth deformation fields. And we saw that we can accelerate the registration process by a factor of 2.5 on an average. The ongoing work is focusing on designing a diffeomorphic interpolation scheme which is suitable for non-parametric registration. And we are also investigating the effect of image smoothing along the temporal dimension. Recently, we have published our initial results in the ISBI conference 2020. I thank you for your patience and listening.